Happy Easter, everybody. You can see that I am wearing my Sunday best. Looking good. And today we're going to make a video for you based upon this list of stuff that we would be going over had we been together. I gave you 4 videos so far on the first, about 2/3 of the words on here, 2/3 of material. But the last third is really important. Several questions that you'll have in next week's academic adventure will be based upon this material down here. This absolutely multiple choice kind of things. You know, last week we worked on problem solving, and basically all the problems are on those problems that you'll have in your exam. A lot of multiple choice coming out of this section, and this is, well, important stuff. What are called quantum mechanics for chemistry. And what we have down here, I'm going to start off by just kind of a little bit of review in this section here on Bohr atom, Heisenberg uncertainty principle, blah, 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 blah. Then we'll segue right into the first part on quantum numbers. Okay, so you should have watched the videos on the Bohr atom. The Bohr model. Bohr basically said that you've got a nuclei, or in this case a nucleus, and you will have energy levels where you'll find electrons, and the farther away you are from the nucleus, the larger the energy level, the more electrons that you can put into those energy levels. And that's fine, that's great. That is a true thing about the Bohr atom, that in terms of what is known about the atomic structure today. In fact, there's an equation, which was in the video, just a review, I'm sure you watched it, that 2n squared is how you calculate how many electrons in each energy level. So if you're energy level 1 or 2, we can put the 1 in here for n, that's what the n stands for, the energy level number. The 2 goes in here, and we can calculate how many electrons in each energy level. So energy level 1 could hold 2 times 1 squared. Get your calculators out, here we go. 1 squared, what do you got? It's 1. Times 2 equals 2. So energy level 1 could hold 2 electrons. If we do the same thing for energy level 2, put a 2 in, 2 times 2 is 4, times 2 is 8, we get 8 electrons, and so on and so on and so on. The farther out you go, the more room there is, the more volume there is for these electrons to kind of be hanging out and chilling. Okay. There will be more electrons out there. Energy level 3, 3 times 3 is 9, times 2 is 18, so on and so on and so forth. You can do that math, I have faith in you. All right, so that's the Bohr model. Then Heisenberg comes along and says, yeah, not so fast, Bohr. You've got these things locked into these orbits. He's got them quantized, in other words, at particular energy levels. You can't hang out in an energy level 1.5. You're either in energy level 1 or energy level 2. That's kind of where our quantum comes in. You have to be in a specific energy level, not in between. You can't be in between. Try climbing a ladder, stepping on the first rung, and then trying to hang out between the first and second rung and see how that works out for you. Okay, you can't do it. You're either on rung 1 or you're on rung 2. You're not in between. Okay, so we've got our Bohr model, which is a pretty decent model. It is a pretty decent model. And you probably learned that when you're in middle school. It's decent. It's a good teaching model. It's not quite accurate 100%. There's more to it. One thing is that these electrons aren't locked into these orbits. In their energy levels, they can move, groove, shake, and bake back and forth. The other thing is that energy levels have now been found to have sublevels. So each energy level is broken down into sublevels. And that's basically what I want to jump into here. Okay, I hope that today's lessons or videos will make some of you go, bing! In other words, light bulb, go off in your head. Okay, we're going to show you a periodic table in a little bit. Why is the periodic table set up like it is? More on that in 2 weeks, but for today, it is set up, you know, somebody just didn't decide, I want to make a periodic table, and it's going to look like this. Doggone it, we'll pull some stuff out down here, right? That's what I want it to be looking like that. No, that's not how it works. Okay, periodic table is set up for a reason, because nature kind of is a description of what nature does with electrons. So these electrons can live. The electrons aren't really alive. How do you know? You've never actually met one. That's a good point. I guess I'm making an assumption here, and I shouldn't assume, but I'm still going to assume they're not alive. Okay, these electrons live in certain energy levels and what are called sublevels of each energy level. And the way it works like this, let's cut right to the chase. What do I need to know? This is who you people are right there. That's who you are. You're bottom line kind of people. bottom line. That's who. Okay, go on. Okay, so energy levels. Well, if we were to look at energy levels, here's a nucleus of an atom down here at the bottom. Energy level 1 is somewhere here, energy level 2, energy level 3, yada, yada, yada. There are sublevels to these energy levels, and it corresponds to what energy level number you are. If you're energy level number 1, then you have exactly, this is easy, 1 sublevel. That's pretty easy to remember. So you have 1 sublevel, which means basically you have 1 level, because we only have 1 sublevel. It would be like a 1-story apartment building. You know, what floor of the apartment building you live on, Billy? Well, there's only 1 story, there's only 1 floor, so I live in that one. Okay. Energy level 2 has 2 sublevels. And these sublevels actually have letter designations to them. I know called quantum numbers, but they're actually letters that are assigned to them. The first sublevel is called an S sublevel. It's the simplest sublevel. S is not for simple. I suppose you could think of it that way, but it's not why it's called S. Then energy level 2 has an S sublevel and a P sublevel. Energy level 3 has an S, a P, and a D sublevel. And I ran out of room here, but let's say over here we put energy level 4, which of course would be way out here off my board. Energy level 4 has 4 sublevels. And that would be an S, a P, a D, and an F sublevel. All right, you people are relatively intelligent people. You can see that the S is always the first sublevel in any energy level. Then if you have room, the P would be next. Then if you have room, so in other words, if you're getting to be a bigger and bigger energy level, they have more room for these sublevels, you end up going P and then last, D, I was P before, D and then last F. So energy level 1 has 1 sublevel, 2 has 2 sublevels, 3 has 2 sublevels, 4 has 4 sublevels. What about energy level 5? How many would that have? Well, if you had an atom which was large enough and had enough electrons that someone would have to go in energy level 5, there would be 5 sublevels. What letters are those? Well, S, P, D, and F are your only 4 sublevels. Well, energy level 5 would have 5 sublevels, so what would that one be called? That is correct. Energy level 5 would have 5 sublevels, but that 5th sublevel would never, ever get used. It would never get used. So theoretically it's there, but it never actually gets used. And we'll see why that is true in a little while. We'll find out why that is true. That there is no 5th sublevel designation because it never gets used. Now, you might say that this means S is for simple. Actually, no. These actually do have names. Why they're called SD or SPD and F is not just some arbitrarily. Somebody just decided to, I'm going to use those letters. It means simple, spherical, principal, diffuse, and fundamental. You don't need to know that, but there is actually reasons why these sublevels have those particular letters assigned to them. Okay, so these sublevels become important because within an energy level, electrons can kind of hang out, chill like a Vilio in these different sublevels. And why would they be in certain sublevels and not in others? Hold on there, Billy. We'll get to that. Okay, that's a good question, but we'll get to that. All right, let's take a look at these sublevels, though. Sublevel S, P, D, and F. Those are our 4 potential sublevels. Sublevel S, as I said before, you can think of it as being the simplest one, but that's not why it has an S as a designation. It's called spherical, meaning that's the shape of the sublevel. It can hold up to 2 electrons. It's the simplest and smallest sublevel not, and go think about it being an apartment building, kind of like this. And different apartment buildings have different floors to those apartment buildings. And some floors have more rooms than others. It's kind of a way to look at it. This is the ground floor. It only has 2 rooms available to be rented out. Maybe the other rooms, the space down below has to do with office space and maybe laundromats. So I'm just making an analogy here. But anyways, P, that sublevel, can hold up to 6 electrons. A D sublevel can hold up to 10 electrons. Do you see the pattern? 2, 6, 10, 14, correct. So 14 electrons would be how many electrons could be held in an F sublevel of an energy level. And that's a big sublevel. It has a lot of electrons that it can hold. Okay, so that's important to know those S, P, D, and F in the amount of electrons they can hold. The thing we have to get into now is talking about what's called an orbital diagram, orbital filling diagrams. If I'm looking on a sheet of paper right here, you will see that we are now into the orbitals and an orbital diagram. So what I'm going to get into is talking about what is an orbital diagram, what's the point of it? Okay, the point of an orbital diagram is to show where the electrons are around an atom. And the reason we want to do that, it'll soon explain why a lot of chemistry works. It's actually important to explain why chemistry works. So let's get into building an orbital diagram. Now, what's an orbital? I keep saying orbital. What's an orbital? An orbital is a place, you represent an orbital by just a horizontal line, that 2 electrons can hang out. Hanging out, electrons. 2 electrons can hang out in an orbital. It can hold 2 electrons. So it's a region around the atom where 2 electrons can kind of coexist. These electrons that we're going to draw into the orbital are represented by arrows. Arrows? Why arrows? I guess somebody decided that was a good way to do it, okay? Don't think too much about it. But an arrow represents an electron in an orbital, that horizontal line. I think about it as kind of like 2 roommates in a room. Okay, there's a room here, and there's space for 2 of them to live together, to coexist. Now, why did you draw one of those arrows upside down? Did you do that on purpose? Absolutely, I did. Because the reason is electrons have certain spin direction. They actually spin. They move, groove, shake, and bake all over the place, and they're also spinning around. They're spinning. And this represents a spin direction, clockwise and a counterclockwise spin direction. Now, it's not important that you know that in terms of physics. It kind of matters in that spin directions lead to things like magnetism and all kinds of nifty things when you spin around. Charged particles, you get a magnetic field produced. But that's beyond what we need to know. What we need to know is that they will spin in different directions. That's why we have to put one arrow up, one arrow down. It's the only way they're going to coexist. They will not coexist spinning in the same direction. It's deep, and it gets into a lot of physics that, again, you don't need to know. Just stay focused, people. Stay focused. Okay, so that's an orbital, and these are the 2 electrons we're going to put in an orbital. You cannot have 3 electrons in an orbital. Can you have 1 electron in an orbital? Absolutely. It's possible to have 1 electron in an orbital. We'll soon see that. That's an important thing. And is it possible to have no electrons in an orbital? Sure it is. I mean, you can have an orbital and not have anybody living in it. It's like you can have an empty apartment in an apartment building. Not everybody has to live there, but you can't have more than 2. All right, we're going to stop this video at this point. Otherwise, it takes forever to load. It's already 14 minutes. So we'll stop here and pick it up on the flip side. Flip.